Tanisha, please proceed.
Good evening, everyone. Welcome to the Centenary Celebration of the Department of Mechanical Engineering, IIEST Shibpur. Today, we are here for the 32nd lecture in the Centenary Lecture series to be delivered by Professor Bandyopadhyay on the topic Thermal Spraying, a technology for adding layers. Today's session is to be chaired by Professor Oshim Guho, Assistant Professor in the Department of Mechanical Engineering, IIEST Shibpur. Sir, over to you.
Thank you, my dear student. We all are eagerly waiting to hear the illuminating lecture of Professor Bandyopadhyay on thermal spraying. But before that, I should formally introduce him. It gives me immense pleasure to introduce Professor Bandyopadhyay to you, a very, very popular teacher as well as an eminent researcher. Professor Bandyopadhyay obtained his bachelor's degree in production engineering from Jadavpur University in the year of 1990. He has served Steel Authority of India for 1 year as junior manager. Thereafter, he joined the M.Tech program in mechanical engineering at IIT Kharagpur. After successfully completing M.Tech degree, he has done his PhD from Mechanical Engineering Department, IIT Kharagpur, in the year of 2000. He has worked as Swiss as the he has worked at the Swiss Federal Laboratory of Material Testing and Research during 2002 and to 2003 as a postdoctoral researcher. Professor Bandyopadhyay has taught in several engineering institutions, including Bengal Engineering and Science University Shibpur, presently IIEST Shibpur, from December 1998 to September 2005. He joined the Mechanical Engineering Department IIT Kharagpur as assistant professor in 2005 and started his research group in thermal spraying. He has been serving as a professor since 2015. So far, he has supervised 12 PhD students, authored more than 100 articles in peer-reviewed journals and conferences, participated a number of international collaborative research initiatives, and investigated many sponsored projects. His primary research focus is thermal spraying. Apart from all these, he is no less than my elder brother. He guided and helped me a lot during my initial period of teaching career when we were colleagues in this institute. With this small introduction, I would like to invite Professor Parthopratim Bandyopadhyay to deliver his illuminating lecture on thermal spraying. Over to PPB. Dr. Bandyopadhyay, please.
Can you hear me? Hello?
Yes, you are audible.
I'm audible?
Yes.
Okay. So,
And visible also.
thank you, Asim. You have been very, very generous.
Most
The
welcome.
pleasure is mine to be able to speak to this august gathering. As said, I'm not an alumnus of B College. I'm from the so-called rival institution, Jadavpur University. But connection with B College was strong. I served there for 7 years. Then after I came to another organization, no ties were not severed. I'm still in contact with my friends in B College. From time to time, they invite me as examiner. Very recently, they have honored me as a member board of studies. So the pleasure is mine. And now I'll share my screen with your permission. Kindly tell me if you, okay, just 1 second. Can you see the screen?
Yes, sir. Fine.
Yes.
Thermal spraying, a technology of adding layers. This is something we do. Now I will change the screen. Sometimes there is a time delay. Please let me know if you see my next screen. There's a problem here. Just give me a second. Can you see the second screen now?
Yes.
I'll take up from here. Now it's okay. From now onwards, it will behave. Okay. Imagine a situation, a simple situation. You start with a 60 millimeter diameter shaft. And somebody asks you, reduce the diameter to 59. What will you do? Simply remove 1 millimeter, simple thing. Now suppose somebody asks you to increase the diameter. What will you do? Okay, therein thermal spraying comes in. It's an additive technology, though it does not belong to the club of so-called additive manufacturing, but definitely it's a technology of material and dimension addition. Okay. Other than dimensional restoration, what can you do? We can add wear protective layer. We can have a thermal barrier coating. We can have protection for electrical insulation. We can have protection for corrosion, so on and so forth. I will talk about them. What we do in thermal spray? We start with a precursor material. Either it's a powder or it's a rod. Okay? And we have a heat source. We marry them where this precursor material is consigned to flames. They melt, and then somehow they are projected to a substrate or a target. Okay. If you melt a small particle and project it, what will happen? You will get a deformed particle. This is known as a splat. This is known as a splat, unit of thermal spray coatings. Then one layer will be occupied with splat, then next layer, bead by bead, coating will build up. To what extent? That depends. It's not a so-called thin film coating. I cannot go to half a micron. Minimum thickness will be around 25 microns. How thick? We can go up to several millimeters. The industrial standard is something to the tune of 300 microns. Okay. Now, if you see a coating in a cross section, it will look like this. I have a substrate and I have a top coat. In between, there's an intervening layer that is called bond coat, offered many a time, especially for ceramic top coatings, to reduce the gap of thermal expansion coefficient between the substrate and the coating. Okay. How does it work in reality? Here, I have packed inside everything inside a cylindrical package that is known as a gun. It has a snout known as nozzle. Everything means gases, oxygen, compressed air, arrangement for feeding powder or rod, everything. that is held in a manipulator, it can be manipulated. How? Wait a minute, please. This video doesn't have sound. This is the flame that comes out. It pushes the powder inside and you get a layer. This coloration is due to a different layer that is built up on the cylindrical substrate. This is how it is done. Let us go back to history. This gentleman, Dr. Max Ulrich Schupp, is credited with the glory of inventing the process. He's an inventor. He did a lot of things, including joining of aluminium, or he invested a lot of time in development of lead acid batteries or accumulators. He did his work in Zurich, in France, in Moscow, in Ukraine, many places. Mostly in Europe. He was close to Tolstoy. And late in his life, he went to America to meet none other than the other great inventor, Thomas Alva Edison, but their collaboration, well, it's not well known. Okay, one day, he found his son is playing with a gun that pushes lead pellet. These lead pellets, when impacts on a metallic substrate, it sticks. This idea struck, and the idea of thermal spraying was born, which he took up and gradually developed it in various forms. Initially, he had a heat source, a flame. Onto it, he put powder. Next, he took up a rod, melted it with a heat source, and used compressed air to blow the molten particles to the target. There's another type of form where he used a gun, packing everything together. A patent was granted in 1913 after a lot of fight. He had to invest a lot of time convincing the jury that thermal spraying, in fact, is an unique process. It is not a copy of a predecessor of another process, and it's well different from painting. Finally, a patent was granted. Thereafter, it took off. We had the first stationary metal spraying plant. Then from powder to we make solid ware. The process called metallizing was born using flame, oxyacetylene flame. In 1939, a job shop was opened. Now customers can come, get their products, old product refurbished with a coating and go. Earth spraying came in similar time. In 1950, people started talking about plasma spraying, detonation spraying, low pressure plasma spraying involving vacuum in a vacuum chamber. And HVF came in the year 1980. Thereafter, we have new kits in town like cold spraying and HVF. Now, what are all these? There are different variations of thermal spraying. It's a domain. Under this subject, we have got various processes. They're similar, but not exactly same. Let us have a quick look. When we have a chemical heat source, means either oil, mineral oil, or a gas like hydrogen or acetylene, we get these processes. We get these processes, either powder and where consumables are used. When you have got an electrical arc, we use these processes, arc and plasma spray. But suppose we do not want any heating at all, we do not want any melting. Is it possible? Like the lead pellet? Yes, that is also possible in a modern process known as cold spraying. Okay. Let us see what are these processes very briefly. One second, please. It's creating some problem. Yeah. Here, everywhere we have an encasement, the gun casing. Okay. What we do here, centrally pass the wire. It's possible to pass powder also, either externally or internally. Either externally or internally, it's possible. And here we can pass in fuel gas, oxygen. They are passed through these chambers, and we also have compressed here. This is how it works. We pass on the fuel gas, set the mixture ablaze, advance the wet tip melts, we advance it bit by bit, and the compressed air catapults the molten particles to the target. Target is at a safe distance away. How much? Depending on the process, depending on how much heat we inject, it can be 100 to 300 millimeters. One can use accessory cooling for this substrate as well. So it generally remains cold and do not undergo any distortion. So these processes are known also as cold process. Okay. Its cousin, big brother, HBF. Process is very similar, but this time we put in either liquid fuel or gas fuel at a very high pressure, or oxygen at a very high pressure, and set the mixture ablaze. It is allowed to remain constrained for a while in a long chamber so that pressure builds up, and when it exits through this narrow nozzle, it goes out at a high speed. So we can get a very dense coating here. Of course, time of flight is low, so we cannot melt high melting point solids like oxides. It's good for metals. It is good for carbides, where we have thin layer of metal covering the carbide particles. It's possible that way. It's well known. It's a commercial success story. One question. Bidut.
Yes, sir.
Am I clearly audible?
Yes, you are.
Okay. that I need to be assured of it. Should there be any problem, don't hesitate to stop me.
Yes, sure.
So that is HVS. Next, another guy. We call it detonation spray. What is that? We have a tube. Okay. Inside the tube, we have installed a spark plug. We push in fuel gas and oxygen and start exploding it at a rate of 2 to 4 Hertz. It explodes, high temperature and pressure generates, powder particles inside are carried, are taken afloat by the expanding gas and carried to the substrate. Once again, a very dense coating, but it's a metal coating, not meant for oxide. Also, process is noisy and a little bit of hazardous, and it's not available commercially. One must go to a designated job shop to get it done, but it's a very good process for metals. Next, my favorite, this is what we do. Okay. What we do is something like this. Once again, an encasement is there. It's an electric process. So we have an arc. We have a hollow anode. Hollow anode. This anode is hollow. A hollow anode. Into that we put in a bullet-shaped cathode. This is a bullet-shaped cathode. We put in inside. Okay. There's an annular gap through which we pass in some gas. We have to chill the entire gun, so there's an arrangement for cooling water. Very important. We have arrangement for putting powder and carrier gas. Okay. What we do? We start an arc. Gas in contact with the arc will ionize. When it is ionized, it conducts more electricity, so increase current. More ions and electrons, more current, more heat, more gas, more current, more heat. In a small volume of gas, I keep on injecting a large amount of energy. Commercial available plasma is available at 50 to 100 kilowatts. It can be more. One constraint is heating. If the temperature is too high, the entire encasement electrode and nozzle will melt away. So procedure is good for making a sun if you can contain it. Okay. Here it's an electrically powered source. We can tune the power. So depending on the power, we can melt polymer, ceramic, or metal. Substrate, as said, is gold, so it can be metal, ceramic, or polymer. So we have metal, polymer, ceramic on metal, polymer, ceramic. Virtually anything on anything. That is the beauty of the process. Speed is reasonably high, and we can get very high temperatures. Its younger cousin is this. Simple to understand. Arc spring, develop long back. I have a positive wear, I have a negative wear. Bring them close together, get an arc. Tip will melt away, compressed air jet will do the rest. Meanwhile, keep on using rollers, keep on advancing the wear. Very good for electrically conductive wares. For everything electrically conductive that is available in a wear, you can develop coating very quickly. One of the new kids in town. What we do here? We paid helium, argon, nitrogen gas at a very high pressure. How much? 50 bars, 60 bars, 40 bars. Normally not below 40 bars. Okay? Put it, heat it to a gentle temperature. For example, you are spraying aluminium, melting point is 660. Don't heat it beyond 300. You have a powder feeder, pass it to a converging diverging nozzle at very high speed so that the particle deforms and sticks to it. No melting, no oxidation, no phase transformation, layer is compressive. Of course, it's not meant for brittle materials. I have a video, it's similar. Very good. They're deforming and sticking. It's of course it's artist imagination, but it is something similar. I have said many things. Gas at very high pressure, distance 100 to 300, temperature, cooling. These are so-called parameters of spraying. Look at it closely. You take, for example, the feedstock particle. What's the particle size? 5 micron or 50? What's the shape? Is it angular or round? Is it a hollow sphere or a solid sphere? Is it an agglomerated powder or a solid powder? Okay. What kind of arc power you are using? 50 kilowatt or 100? Nozzle diameter, how much it is? 5 millimeter or 10 millimeter? Okay. We have injector also, there are many parameters. We have parameters for working gas. What's the pressure? What's the flow rate? What's the type? Are you using nitrogen alone or nitrogen along with hydrogen? What happens when helium is injected? This is for plasma. If you take HVA for cold spraying, other parameters will come into play. For example, cold spraying, gas pressure is a very important parameter. Gas pressure is a very important parameter. How many parameters are there? 10, 15, 20, 30. Compare it with a standard manufacturing process like metal cutting. We find it difficult to control 3 parameters, speed, feed, and depth of cut. How will you control 30? To key. Okay. Is there a solution? Look at the process. I am getting this warning. Is the gun? Powders are ejected from there. Particles. They melt and they deform. Whatever the parameters may be, it is the state of powder before impact that determines successful coating. What is meant by state of powders? There are only 2 derived quantities derived out of 30 parameters. It's temperature and velocity. Temperature too low, we'll get an unmelted particle. We have an unmelted particle. Okay. Or we get pores, or we get particle bounce back. If you have very high velocity, will show, splats will badly deform. So these two are important. So once we can measure the particle velocity and temperature there before impact, we really do not care what parameters brought this has given us these two derived quantities. These two derived quantities we looked at. So is it possible to tune the parameters and reproducibly produce temperature and velocity in a close range? That's the question. There lies the solution to our problems. It is possible. It took nearly 100, more than 100 years to achieve this target in a laboratory scale somewhere in India. Still, it has been done in laboratory. Do not know when it will find the light of the day in an industrial setup. What is the problem? Problem is that it is difficult to separate particle temperature from velocity. Why? Imagine you want higher particle temperature or higher particle velocity. What will you do? You'll simply increase the arc power. Temperature will increase, of course, but at the same time, at the high temperature gas will expand faster and carry the particles faster. Velocity will also increase simultaneously. That is something you never wanted to start with. They are coupled. Is it possible to decouple them? As said, in the laboratory scale, yes. And well, it was done in 2022 for the first time to our knowledge. Okay. What we did here, what we achieved here is like this. We cannot keep the velocity exactly constant, but if we confine it to a very narrow range, while temperature could be varied. Where the temperature could be varied. We have taken an alumina particle and melting temperature is around 22. Okay, so we have varied the temperature. Keeping close to 22 doesn't help because most of the cases particle will be unmelted. So you superheat the particles a little bit. Similarly, we kept temperature nearly constant, not exactly constant, and we could vary the velocity. It was made possible by rigorous experimentation. Have a look at the velocity and temperature. Okay? Temperature. If you increase temperature, you'll melt it. Too low a temperature will leave particle unmelted. But if you go too high, well, you are wasting heat, number one. And number two is that for low melting point particles, some particles can vaporize. We can give temperature, particle temperature to 3000. We don't need a temperature of 3000 for melting iron or nickel. Forget about copper or aluminium. So deposition efficiency will fall if you insist on too high a temperature. Velocity, alumina particle 197 meter per second. See the shape of the splat? And you carry it to 247, see the splat, it is deformed. A high velocity will exacerbate the properties of the coating as it has been found. Okay. What happens when you spray with an increase in particle temperature? In the range, in this range of the experimentation, it was found while the velocity is narrow in a near constant, we could see that with improvement in particle, we got improvement in properties like fracture toughness, elastic modulus, and hardness. Similarly, with increase in velocity, initially porosity decreased because of good particle shape. But when you increase velocity too much, as shown previously, we get a distortion in the splat shape and we get a increase in porosity. Hardness also initially increases, but with porosity it decreases. Same thing goes to for modulus of elasticity. So temperature and velocity must be decoupled so that we can get rid of the load of baggage of parameters, and they should be closely monitored. This process requires very stringent process control. We talk about velocity and temperature measurement. Yes, there are commercial setups available. They're a bit expensive maybe. We use a couple of Canadian setups. There are European products available off the shelf on the market. Okay. For measuring temperature, what we do, we sense the temperature of the particle, we detect the particle, sense the temperature of the particle for two wavelengths and measure their intensities. Once we get the intensities and the wavelengths, from a correlation, we can get the surface temperature of a particle. For velocity measurement, we have to track a particle for a small distance, plot the time, distance known, and we can get the average velocity before impact over a short distance, which is close to the real instantaneous velocity. Okay. Kindly note, dealing with these instruments are also always not easy, but it's possible. What we spray? These materials, almost all metals with specialized alloys, polymers, a host of carbides, and host of ceramics. As said earlier, polymer ceramic metal and polymer ceramic metal. You give me a powder with an interesting property that does not decompose at high temperature, one can get a functional coating with interesting properties. So that way, with time, the explanation, the applications will more and more newer applications are expected to come. And another advantage is that compared to thin film coatings, they usually require closed chambers, closed environment. Here, it's possible to do it in atmosphere, and one can literally spray quickly on square meters of substrates. So that's the advantage one got. The thickness is also can be pretty high. As I said, 300 micron is pretty standard. Applications. Many applications are possible. It's for wear, for corrosion, for electrical insulation, as thermal barriers in turbine blades, decorative, medical implant, and also biological coating possible. Can I further improve it? There are mechanisms. You can produce something that gives it hardness, gives it stability, gives it strength. For example, you can put in carbon nanotube, you can put in diamond. You have good wear property. Add to it some solid lubricants that will give you lubricity as well. You can take an aspirate coating and post-process it using some laser remelting, using some heat treatment or spot cleaning. They are possible. Okay. Now there are some issues here that I'll briefly address. First, and you want to have a lubricating coating, add tungsten sulfide. You want to improve the hardness. With bronze, we use diamond, bronze and higher diamond mix well. You want to have improvement in wear properties of alumina, mix CNT. Now there is a problem. How do you mix them? In a jar mill, by mechanically shaking, you can mix them. Difficulties are there. For example, in use, they can gravity separate. Or if you take some materials like carbon nanotube during mixing, it can break. So how will you mix them? An example of a process, we call it heterocoagulation. We take yttria stabilized zirconia hard coating. Onto that, we wish to put in barium fluoride, high temperature solid lubricant. If you try to mix them, they tend to segregate. What will you do? You bring in another chemical here. It's called CTAP, a surfactant. They're available in detergents. And you bring in here SDS, another surfactant. Okay. This surfactant here surrounds the YSZ particle and gives it a positive charge. We technically call it positive zeta potential. On the other hand, SDS provides it a negative charge. What's the advantage? Well, in a charge-free environment, if you put it in water, they tend to agglomerate and quickly decant it, quickly hit the bottom. But if you add charge to them, they will repel each other, not agglomerate, and they tend to remain in solution for a longer time. Typical use of surfactants. Now, you mix, keep this mixture ready, positive, this mixture ready. Add them up slowly. What will happen? Positives will get in touch with negative and lose charge come to zero. When they lose charge, they can agglomerate and hit the bottom of the container. No shaking, no breaking. Get a perfectly homogeneous, stable mixture that you have to dry out. So this is one procedure for powder mixing. Next, you picked up this ceramic with this solid lubricant. Okay. Will it work? We have to keep an eye on the compatibility as well. How it is possible? Take an example. Instead of BF2, I have taken CF2 this time, similar thing. I took aluminum and titanium, the standard material. I put a coating. Onto that, we put a globule of calcium fluoride made from calcium fluoride powder. We put here. The melting point of calcium fluoride is 1418. I heat it up to 1450. See what happens? It is completely dispersed. We say the weightability of calcium fluoride is good with alumina titanium. Try similar exercise with YSZ. What was round before hitting just blackened. It didn't spread over. So picking up additive is also another exercise one must be very, very careful about. Okay. Now, after doing the composite coatings, what do we do? What do we get? What kind of improvement do we get? Here you see, I have a simple tungsten carbide. I put some CNT into it. The wear coefficient is a measurement index of wear, how quickly material is removed, that reduces, wear resistance increases. In each case, this is one type of carbide, this is another type of carbide, we get a reduction. With aluminum oxide also, we get reduction. It increases with percentage of carbon nanotube. But we cannot increase carbon nanotube indefinitely. That will create some other problem in powder flow. 2% gives me very good results. Okay. Similarly, for wear purpose, we can use molybdenum coating with diamond and without diamond. With diamond, we can use bronze coating as well. This is for wear. Same improvement is also possible with lubricity or whatever we used to. If you have a suitable additive that mixes well and that is compatible to the matrix, and that gives you some good properties, it's possible. Another restriction is a decomposition and high temperature. That is not permitted. Next, post-processing. Simple. We had a coating very porous. Melt a layer, top layer with laser. Big defects, cracking will be there, but pores will go. Okay. Porosity initially was 6%. After that, it's reduced. After laser remelting, the indentation fracture toughness also improves. Hardness increases, so does the elastic modulus. Similar observation is as observed for chromia coating, not only aluminum oxide. Okay, but the cladded layer must not be too thick, not cladded. Remelted layer must not be too thick. During contraction, we are getting a melt pool. If it contracts, if it's too thick, there's a chance it will come off. So a scope of optimization is there. But one can improve the property with this type of post-processing. Another perennial questions. We have a coating and a substrate. The substrate doesn't melt, coating melts. As long as it doesn't decompose, we can spray it. So anything or anything. We do not talk about metallurgical compatibility at all. So how coatings adhere on the substrate? Can you measure it? Yes. How do you measure it? We take a substrate and coat, glue both ends with two anvils and pull them apart. If the coating breaks, glue is usually stronger. Now very strong glues are available in the market. If the ceramic coating goes up to 25 to 40 MPa, it's okay. For metallic, we got to 60 to 100 MPa. It's okay. As long as it works, it serves the purpose. We do not get into it. Why? One explanation is that the interface between the coating and substrate is too thin. It's difficult to investigate. We carried a small investigation somewhere. This is an example. Okay. Before that, there are several possibilities of the bonding. It can be mechanical interlocking at the rough surface. We make the substrate rough initially by grit blasting, or the bond coat, if you spray on the grit blasted surface, it has a rough surface. Or it can be metallurgical chemical bonding. We don't know. In this investigation, this is published. One can find it. We measure the residual stress profile of the coating. The top coat, we start from the top coat, we get into the bond coat and slowly get into the substrate. We get near zero stress at the top coat and we gradually go inside and get a strong negative compressive stress. When we come to bond cord, we get low compressive followed by low tensile stress. In the substrate, we have low compressive to low tensile. This is a bit intriguing. How can there be a phase discontinuity in the continuous material? This should not be stable. One surface should come off. There must be a continuity. Then what is done? Initially, layers were removed at 20-30 microns from the top coat. Then as the interface of bond coat and substrate is approached, layer removal of 5 to 7 micron was done. Okay. So what is there at the substrate, top coat? Aluminium oxide. So near the substrate inside aluminium, we are supposed to get aluminium peaks in the X-ray diffraction. That's what we got. Then we gradually 5 to 7 microns we go in. We go in slowly, and after some time we start getting nickel peaks from the nickel aluminide bond coat, and thereafter after a certain time we do not see naturally aluminium oxide peaks. We get only nickel peaks where we are well inside the bond coat. Okay, from top coat to bond coat. While we expose the layer, we measure the stress. What we see this time, that initially somewhere here, it has a high negative stress. Then negative stress remained negative, and gradually it raised its head and became similar, continuous with that of the bond coat. This is a macroscopic view. This will not tell us the story. We miss many data. One has to do very minute deprofiling to see stress continuity in both top coat, bond coat, and bond coat substrate interface. What is happening is like this. This is the bond coat rough surface. We have a pore in top coat there. Okay. So what will happen? This is a rough surface. Asperities do not have any stress. They are stress free. But when you put in top coat, pour in top coat like you do in casting, something similar, this will have, depending on the thermal expansion and heating, either a tensile stress or a compressive stress. Either a tensile stress or a compressive stress. If it is tensile, it will push on these flanges, on the outer flanges. Okay. If it's a compressive stress, it will try to shrink and it will put pressure there in some other side of the thread-like asperities feature. Okay. So in other words, this is the stress of the top coat that pulls the stress-free asperities towards its own same stress level. And ultimately, when we go deep in the bond coat, its stress behavior dominates, and we get a mild tensile stress as reported in the macroscopic view. So in this investigation, it appears that bonding is predominantly mechanical. But since it remains to be seen whether some chemical or metallurgical bonding has been taken place. Going to the thin bond coat, there's no diffusion zone to speak of a few microns. It's difficult to find out the metallurgical nature of bonding. It will be an interesting investigation for the future. So here are in conclusion, what we see, thermal spraying is a process. We can make parameter selection only two this time, simplify parameter selection with adequate instrumentation. There are different processes we can cater to. There are large number of applications and the scope of property improvement is always there. It's a growing field. It's expected to grow over the next few decades. Thank you. Thank you for your patience. Vidut, I can't hear you.
Yes, sir. Professor, go please.
Session chair is muted or not?
He can unmute himself. Professor, go. Please unmute yourself.
Is there any difficulty with session chair?
I can hear you clearly and I also can see you. I have no difficulty.
So let me check with the sessions.
Well, if session chair is not available or maybe some connection issues are there, I think we can open it for discussion in the house. So I would request the speaker to accept queries.
I will.
Yes, so it's open to the house. And Middu, do you please see if session chair is available or not? Yes, our usual first response comes from the senior most member of alumni, Achyuta.
Yes, sir.
How did you enjoy it?
Yes, I was listening with great interest. And I must tell you, sir, Dr. Professor Bandyopadhyay, it is rather difficult to follow. For me, I am listening to all these lectures for all from the starting day. This lecture is rather somewhat difficult for me to follow. This is
Difficult. Sir,
Yes,
you are doing wonders for my confidence.
no, sir, no question of confidence. It is my failure, my limitation of knowledge base. But I have got few questions for you, sir. One is,
Yeah.
in which laboratory you did this work? This is the developmental work, and this will go on working. So, in which laboratory, either in India or outside, you did this work? One, and then whenever, I mean, I have got certain doubts in my mind. Whenever we are thinking of plasma spray, molten metal gets molten 26 degrees, 2600 degrees centigrade, that kind of values, then how the polyamide or polyethylene particles will behave, why they will not burn out? This is the second question. So first, let me finish, sir. First is this where laboratory, then why the polyethylene and all these things will not burn out. And second is, since this is in the, I mean, this is quite old, you say now it has reached 50 years or something, but still, due to the porosity thing, it must be a very, very difficult subject to handle. So these are my three observations, sir. And I must say my knowledge base is so poor. I do not know much about it. I heard about it. Only thing is, sir, one more statement, that we in our factories we always did zinc coating, hot metal zinc coating. But that we knew the coating, due to the positive things, the coating need not be continuous, but it will serve the purpose of protection, zinc coating, spray zinc coating, not deep zinc coating. So that we know. But in this case, to use this metal, the porosities will be very important. So that's the end of my statement, sir. Thank you.
Sir, I will respond to your queries. Number one, well, I had the fortune to work in several laboratories across the globe, in both sides of Atlantic. But these days, mostly I work in my laboratory. I have a laboratory of my own in Kharagpur, but I do collaborate. I do collaborate with peoples abroad. Okay. I also collaborate in India. Sudeep, is this part recorded? Is this part being recorded?
Yeah, it's
Yes.
recorded.
So, okay, fine. So, fine. So, I have to, always keep in mind that something is recorded and something will be made available to the public. So, I have to tune my speech according to that. I do collaborate with abroad. And yeah, most of the work I do these days in India. Number two, 2600 Celsius and all. Okay. 2600 Celsius and all you don't have to have. I reported the result from a plasma sprayer that gives you a power of 80 kilowatt. You can have a plasma sprayer that gives you a few kilowatts. Temperature can be tuned. And regarding porosity, it's a genuine problem. By going to the basic nature of the process, coatings are porous. So many a times, when you use for it for corrosion, additional sealing of coating using some type of polymer is required. This is true. But again, using some electrolytic process, you can have a thin zinc layer over a surface. But if you want to coat something with square meters very quickly over a few hours, this process you cannot beat. Okay. So each has its own upshots and limitations. Each has its own application domain. Thermal spray caters to some. Thin film caters to some. And of course, electrolytic processes are like electroplating are very old processes. They have their own strong points.
Well, if
Thank you, sir. It clarifies some of my clarities, some of my queries. But anyway, I could understand some, I could not, but that is my failure.
Sir, my phone number is available with Professor Ghosh. My email is there, and it's in public domain. You can get in touch with me. I'll try to satisfy your queries individually. And also over the telephone, and we can be much more frank and free. We can talk in greater lengths, and we can take more time.
Thank you,
And
sir.
one thing I agree with you that yes, the subject is difficult. It's not easy. You are taking powders, you have got so many parameters, you are relating them.
particularly when you enter the set of parameters.
Yeah, they are difficult. And when you are trying to explain addition, when you are trying to launch a new beast in town, a new additive, which you will not know, which you do not know whether work with the matrix materials. As long as you can spray continuously, you can spray an established material, you can work in shapes, you can produce in towns. But the moment you try to change it, problems will happen because you are dealing with a large number of parameters.
When you are describing the initial parts, means perhaps that was flame spraying you were talking about. You started with flame spraying perhaps. So there you mentioned the combustible gas and oxygen, and then some wire or powder material you were feeding. So in fact, I was thinking a similar arrangement was being used for gas cutting, oxyacetylene I'm talking about.
Yeah.
So can we use a similar setup? I mean, and the same set of gas for this configuration or this operation? I mean, it's
The
quite
purpose of gas cutting, the mechanism of gas cutting is entirely different.
rather diverse, but arrangement is looking similar. There also we are using a combustible gas and air mixer, feeding it.
Yeah.
And the
Here
same
you have
arrangement, how the similar arrangement can be tuned to I mean, to be used for deposition just by putting in something extra and perhaps maintaining the condition differently.
Okay, ultimately it's a hate source. One has to try to do it. But if you look at the flame cutting device, a flame cutting torch that is supposed to produce oxygen, provide oxygen at a high volume and a high pressure. Heat energy is something, the principal purpose is to oxidize the metal.
And the flame has to reach that surface also.
And the
here you-
distance is also important because, well, you have to heat up the surface. Here you are not heating up the surface. Okay, you are heating up some materials. So one has to try to first make
But the
the
distance you
materials.
mentioned, the distance you mentioned, perhaps 100 mm or something you mentioned. So it may it so happen that a flame also reaches your substrate, then it is going to destroy your material. So
Well, it 100 millimeter to 300 millimeter is a thumb's rule. It's another standard distance is yet another parameter that you have to set for your particular setup. Objective is to melt and melt the powder so that it heats and sticks. You have to make sure particles do not cool off, particles do not bounce off after cooling, and the substrate is not overheated. These things you have to keep in mind and set your distance. Yes, the range for plasma is typically 100 millimeter. For HVF, we can go up to 300, 330 millimeter. That's the range roughly.
what then is vacuum deposition? I mean, are we considering vacuum in some of the setups here also?
Well, to my knowledge, there was one setup somewhere in the West. That organization is a very big organization. They claim to have a vacuum plasma setup. I do not know what's the status now. I had opportunity to do some vacuum-based processing. I shouldn't call it vacuum. Is evacuate the chamber, then put in some gas at low pressure. Okay, you have to constrain the flame. In vacuum, flame travels very far. But if you can put in nitrogen and argon, you can keep oxygen away and you can constrain the flame as well. So whatever work in vacuum plasma spray or low pressure plasma spray I have done, I did it abroad. I didn't get a chance to do it in India.
Well, queries from our scholars, students, and others, please.
Well,
Sorry,
very
I took
sorry,
some more time.
I got disconnected in between due to network issue. I could connect again.
Oshim, are you speaking?
Yes, I'm speaking.
Be a little louder, please.
Can you please?
I can hear you.
Me?
I
Okay,
can hear you barely. I can
okay,
barely
sorry,
hear you.
I got disconnected due to network issue. I could connect. Very
Okay.
sorry for that. Okay.
You're welcome back, Oshim.
Okay, thank you, thank you. Now, a very small question from me is that this coating, like you are also coating alumina. Now, on cutting tool, if we have coated carbide, is it possible to coat alumina on carbide or on cemented carbide to get a coated carbide tool in this technique, thermal spraying technique? Is it possible?
I have a doubt here. If you think about a standard coating used for cutting tools, they're either by PVD or CVD, very thin.
Yes, those are standard technique. Now,
Yeah, using thermal spraying, you cannot take such a thin coating. You have to build a thicker coating with where splats have joined. The shear strength of the coatings are not so high, so that it can withstand cutting velocity. So it's not so good for cutting tools in general.
okay, thank you so much.
Actually,
Actually,
Professor Bandyopadhyay, if I may add our knowledge base for machine tools and all that, the carbide tip, it is under enormous stress while removing the material. So Fishman's theory of crystallize moving over the cutting edge, I don't think a built-up tool with the amount of porosity that is built in the system can stand the difficult work of being a cutting tool. I have my
Yeah. It's this tool, this thermal spraying is in general does not support cutting tool coatings. In general, it doesn't.
May
Do
I
I
ask
answer
one
your query
question?
or something is left?
Well, thank you. I could understand. Also, you told that it is a functional coating, not a structural coating. It is load-bearing capacity may
Give
not
me
be
1 second. Give me 1 second. I'll just get a headphone. Can you hear me now?
Yes, I can hear you, Professor Bandyopadhyay. I understand
know
it
why.
is.
Even
is-
with a headset,
No, it's I mean something wrong with Asim's microphone. His voice is really low.
Yes, it is due to this laptop microphone is very poor.
hello.
Power, that's right. Yes, maybe but,
My dear Oshim, all
poor
of us
capacity. Yes.
we have tired giving away the laptop thing. We all use additional thing to increase our statement and to listen to properly. That laptop is never, it doesn't give good result. I'm sorry. We use all these headphones only
Yes, I
for
am
the
also
listen.
using headphone. I am using earplug. You see,
That's
I
okay.
am using earplug.
But what about your
I'm also
voice?
using earplug. But
That's fine, sir.
why
That's fine.
voice
What about your
catches
voice?
voice is not through headset. It is through built-in microphone. For
Oh,
your
that
case,
is difficult, sir. We have got a microphone as well in the in the in this.
oh,
We have got a microphone as well.
but in my headset there is no extra microphone.
It does not work really, honestly, with the laptop
Anyway,
microphone.
the
Does not.
session is open. I think
Chairman, I have one question.
yes, viewers can take liberty of putting questions to the speaker.
Yeah.
Chairman is in control. That's fine. Yes, I think we can go ahead.
I have one question. Can I ask?
Please, please. I'll try to answer to my to the
Uh,
limits of my capabilities.
Yeah, I am asking from a different domain, like this NC-CNC control. Suppose the job which is to be quoted is not uniform, like turbine blade, then the distance between the nozzle and the job may not be fixed. So the your nozzle has to be fitted on a some CNC kind of control is required to maintain the gap constant. So
Yeah.
how will you maintain the thickness for a irregular job?
Yeah. So that way the gun is held in a robot.
Okay. The
Gun is
similar
held in a
way.
robot.
So this is first question. Next question is that what is the optimum thickness of the coating for I think the peel off effect? So suppose if we get more coating, then the whole thing will come out. It may happen
Yeah.
so.
Yeah.
So I'm not that much experienced, so I'm asking in that way. So what is the optimum level you decide mathematically or some way?
Mathematically, experimentally, you can devise, you can do that. If you want to do it numerically, you have to formulate it like this. You have to find out first some critical stress value beyond which the coating will either buckle or peel off, depending on whether it's compressive or tensile.
But how will you decide that?
It's
Before the coating,
there is
so
no
how will
there is no way to decide the threshold other than experimentation.
okay, I got it. I got it.
Can
So
I,
initially,
sir,
please.
okay, you please finish, then I have got one counter question.
Okay.
Please finish first.
Okay, so the optimum thickness actually depends on the requirement. Wear coating, normally we go to 300, 400 microns. For certain thermal barrier coatings, people go up to 2 millimeters. It depends on the application. Okay, sometimes we encourage cracking also for thick thermal barrier coatings, where at a high temperature, when it gets heated up, it will expand and contract. The transverse crack absorbs, provide it with some resilience to guard against sudden peel off. But peel off can occur at high pressure, high temperature. It's possible. And each case must be studied individually. As such, no numerical panacea exists today.
Quite interesting.
Sir, I have got one statement here. That is, in one of your slides, you have shown us that the coating layer may develop compressive forces or tensile forces.
Yeah.
But sir, here I have got an objection that for such a thin layer, a development of a continuous compressive or a tensile force very unlikely. It will just distribute itself, and the metal is hot. It is not a cold metal. So in that case, development of a compression or a tensile force is very unlikely in the coating. Which that's my belief.
Okay. Let it just happen something like this. Okay. Initially, you have a cold layer. On the top of it, you have got a hot layer. The cold layer is also not very cold, so as to say. So together they expand. Together they expand. Problem starts when cooling occurs. The metallic substrate has got a thermal expansion coefficient. The ceramic or another metal has got another thermal expansion coefficient. They contract when they come to room temperature from different average temperatures. They contract differently. It may so happen that the substrate during cooling is compressing the coating, making it compressive, or substrate does not contract to that extent as the coating would like to, leaving it in tensile mode. So it is the thermal expansion coefficient, differential thermal expansion that dominates the scenario.
So
Possible.
there must be limitations when you select the pairs.
Of course, there are that's why we bring in bond codes. Sometimes one bond code doesn't serve the purpose. For example, you take turbine blades. Initially, you have a nickel layer. Onto that, you have a chromium-based bond coat. Onto that, you have got aluminum oxide bond coat. Onto that, you put stabilized zirconia for different reasons. One is thermal expansion coefficient. Another is to reduce the chemical gradient because, well, oxidation of the bond coat occurs and the oxidation product are more compatible to alumina than with zirconia. So we put a thin layer of alumina as well. So we can have multiple bond coats.
The variables are too much. It's
Too
a very
many?
difficult subject.
Yes, sir. But then, somebody has to do something. Somebody
Yes,
has to do it. So I am doing it. I
yes,
could
sir.
have done something else as well. But now, when you are working on it for quite some time, you get the hang of it. You don't care whether it's difficult or easy because you are already used to it.
But yes, it's particularly useful when you try to have certain, I mean, set of properties at limited regions on a surface. Like
Yeah.
for example, same thing happens. I mean, same procedure I think is also used for solid oxide fuel cells. The
Solid
ceramic
oxide
coating.
fuel cell is there. Oh, that's another problem. The solid oxide fuel cell cathode materials are extremely hygroscopic.
Hmm.
Extremely hygroscopic. So we can or may not do it in vacuum. That is something else. You need a glove box to handle them, to put it in the feed hopper in nitrogen, close it, and then only you can take it out. I tried to make some solid oxide fuel cell coating.
Hmm.
So without adequate setup, that's once again expensive. It's difficult. Solid oxide fuel cells are a little bit
Using zirconia there.
not zirconia. I use some other oxide, magnesium oxide, and something. I have to check it.
Aluminum and magnesium oxide, a mix of that.
Now I'm on my machine. I can tell you that. I think I can find it. I'll tell you. Just give me a minute.
YSZ is that one they are saying?
I can tell you the type of battery I have used. Wait a minute.
Yttrium oxide they use. Yttria stabilized zirconia, that's why they say.
Wait a minute. For me, I tried to find out something like, oh, cathode is made up of lithium chloride, potassium chloride, and iron sulfide. Then we had a separator of lithium chloride, potassium chloride, and magnesium oxide. And anode is lithium chloride, KCl, and MgO. It's a complicated type of battery. They call it thermal wear battery. They are meant for single use in missile system or something like that. They'll be useful for only once. Tried my hands at it, but well, there are challenges involved. Once I get the setup, I'll try once again.
Thank you. Any more
Sir,
queries?
we must all thank you for handling such difficult jobs so consistently. So our thanks goes to you, sir, Dr. Bandyopadhyay, Professor Bandyopadhyay.
Thank you, sir. It's your blessings. You are a very senior person. I always count on blessings from such senior people. Best good wishes from my colleagues.
Sir, I can give my good wish to you, sir. I have got no right to give you blessings. That we do not think of, sir. Yes, I am quite aged. I am 82 years old. I graduated Shibpur from 1961. That's there. But
Okay.
I am still working, sir. Yes.
I know some of our teachers. I know you know them. I don't know. I think Soilapati Gupta graduated which year? 53.
But
DN Rai graduated. DN Rai graduated in
he,
53.
yes, he is dead. He joined as director Kolani Engineering Institute, Government of India, Government of West Bengal. But he's dead now. Dhruvoda is dead.
Sir, you live longer. You are in good health. You are still enthusiastic. I would like you to see you after 100 years. Cross century.
Don't, don't give me that Obishap.
Yeah.
No, 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 no. We die
We
when
all
I
wish you
lose
long
my.
life. Well,
Thank you.
Chairman, do you have any more queries from other viewers, or else at the end give me another couple of minutes for Thanksgiving? Or let me do that now itself. On behalf of the department and on behalf of the Centenary Celebration Committee, I must thank Professor Bandyopadhyay for taking time off from his busy schedule to present this wonderful lecture and a compilation of his research works here. Very nice. We are really enriched by your presentation. Thank you very much. Let me also take this opportunity to thank our today's session chair, Professor Guho, for leading the session nicely and introducing our today's speaker to the audience. I have one responsibility. We have as a token of respect, we have this certificate to give to our speaker. Here is the soft copy. The soft copy will be sending through email. We do have a hard copy along with a memento, which we plan to hand over to the speaker sometime later, either here in our campus or maybe we have to arrange to deliver it to his address at Kharagpur. So with that, perhaps we have come close to the end of the session. With thanks to, I should also thank our senior members of alumni. Should I have also seen President of Gabishu joining sometime? I'm not sure whether Madam is still there or not. So thank you, everybody. So with that, we will close the session today.
Thank you.